There is a place in the universe where gravity wins, where light, the fastest thing in existence, dares not escape, where time itself slows, bends, and finally surrenders. This is not science fiction. This is not speculation. This is real. Out there, in the cold, silent dark, lie objects so strange, so powerful, that even Einstein himself doubted they could exist. We call them black holes. And they are not just gaps in the sky. They are not empty voids. They are not cosmic vacuum cleaners sucking up everything nearby. No, they are something far more elegant and far more terrifying. They are regions where matter has collapsed into such a tiny point that the fabric of space and time curves back on itself, where the escape velocity exceeds the speed of light. And since nothing, not even light, can go faster than light, nothing escapes. Not gas, not dust, not stars, not signals, not memories, not time. Once you cross that invisible boundary called the event horizon, there is no return. Not for you. Not for anything. In April of 2019, something extraordinary happened. After decades of work, after linking telescopes across the planet, after processing petabytes of data, humanity saw, for the very first time, the shadow of a black hole. It was not a photograph in the traditional sense. It was a reconstruction, a triumph of mathematics, patience, and global cooperation. The black hole, named M87 star, sits in the heart of a galaxy 55 million light-years away. It weighs 6.5 billion times the mass of our Sun. And around it swirls a ring of fire, glowing gas, heated to billions of degrees, racing at nearly the speed of light. That bright ring is not the black hole itself. The black hole is the darkness in the center, the absence, the silhouette, the place where light vanishes. 2 years later, we saw another, Sagittarius, a star, the quiet giant sleeping in the center of our own Milky Way. 4 million times the mass of the Sun, yet somehow invisible until we learned how to listen, how to calculate, how to see the unseen. These images changed everything, because for the first time, black holes were no longer equations on a chalkboard. They were no longer theoretical monsters hiding in the math. They were real, observable, measurable, alive in their own silent, destructive way. So what exactly is a black hole? Let's keep it simple. Imagine space as a stretchy fabric. Now, place the heavy ball on it. The fabric bends. That's gravity. Now, imagine something so heavy and so small that it doesn't just bend the fabric. It punches a hole straight through. That's the idea. A black hole is not a thing in the way a star or a planet is a thing. It is a place, a region of space where gravity has become unstoppable. The boundary around that place is called the event horizon. Think of it like the edge of a waterfall, not a wall, not a surface, just a point of no return. If you're upstream, you can still paddle back. But once you go over the edge, the current pulls you down faster than you can swim. In a black hole, that current is space itself, flowing inward, and the waterfall never ends. Inside lies the singularity. We don't know what it is. We don't know if it's a point or a knot or a doorway or something our physics cannot yet describe. All we know is that our laws break there. Gravity becomes infinite. Density becomes infinite. Time loses meaning. And that is why black holes are the ultimate mystery. Not because they are dark, but because in their darkness they hide the limits of human knowledge. This is where our story begins. Not with explosions, not with fire, but with silence, with absence, with the most powerful force in the universe wearing the mask of nothing at all. Every black hole begins with a death. Not a quiet passing, not a gentle fade, but a violent, brilliant cosmic suicide, the kind that shakes the galaxy. We're talking about stars, not just any stars, not the small ones like our sun that will one day puff up, cool down, and become a white dwarf surrounded by a ghostly shell of gas. No, we're talking about the giants, the monsters, stars at least 20, sometimes 50, sometimes even 100 times heavier than our sun. These stars burn fast, they live hard, and they die young. In cosmic terms, that means just a few million years. While our sun will shine for 10 billion, these titans blaze through their fuel in the blink of a galactic eye. And when the fuel runs out, gravity, which has been held at bay by the nuclear fire in their cores, suddenly wins. There is no more outward pressure, no more heat pushing back. And so the core collapses. In less than a second. Imagine the entire mass of a star, heavier than 20 suns, shrinking from the size of a city down to the size of a mountain, then a hill, then a house, then a room, then smaller than your fist, all in the time it takes you to blink. The outer layers don't just sit there. They crash inward at a quarter the speed of light, slam into the core, and then rebound outward, violently, cataclysmically. That is a supernova, one of the most powerful explosions in the universe. For a few weeks, that dying star can outshine its entire galaxy. Billions of stars drowned out by one final scream. But not all supernovae create black holes. Sometimes the leftover core becomes a neutron star. City-sized ball of pure atomic nuclei, so dense that a teaspoon of it would weigh as much as a mountain. But if the original star was heavy enough, if the core left behind is more than about 2 or 3 times the mass of the sun, then even neutron pressure fails. And then nothing can stop it. Not electron pressure, not neutron pressure, not magnetic fields, not quantum forces, nothing. The core collapses forever, until it vanishes behind the event horizon, and a black hole is born. Now, you might be wondering, what does it look like when a black hole forms? The truth, we've never seen it happen in real time, not yet. Because the moment the event horizon forms, light can no longer escape. So from the outside, it's silent, dark, almost anticlimactic. One moment, there's a blinding supernova lighting up space. The next, the light fades. And in the center, where the core used to be, there's nothing, just darkness. But that darkness is not empty. It is heavy. It is hungry. And it is waiting. Sometimes, if the black hole is born in a binary system with a companion star still nearby, it begins to feed. Gas from the living star gets pulled toward the black hole. It doesn't fall straight in. It spirals, faster and faster, heating up as it goes, until it glows blue, white, ultraviolet, X-ray. That swirling disk is called the accretion disk, and it's often the only way we know a black hole is there, because the black hole itself gives off no light, but its appetite betrays it. So, what is this event horizon? Let's be very clear. It is not a surface, it is not a shell, It is not a wall you could touch or bounce off of. It is a boundary, a mathematical line drawn in the fabric of space-time. Cross it and you can never send a signal back, never return, never be seen again. Not because something grabs you, not because there's a force field, but because inside, space itself flows inward faster than light. And since nothing can move through space faster than light, you are carried inevitably toward the center. Think of it like being in a river. The water is space. The current is gravity. Far from the black hole, the river is calm. You can swim wherever you like. But as you get closer, the current speeds up, until, at the event horizon, the river flows faster than any swimmer could ever move. Even light, the fastest swimmer of all, gets swept away, and beyond that point, the river flows toward the singularity. We don't know what the singularity is. Some say it's a point of infinite density. Others say our math breaks and we need new physics, quantum gravity, to describe it. But one thing is certain: whatever it is hidden, wrapped in the event horizon. Like a secret, the universe refuses to tell us. This is how black holes are born, from the ashes of the mightiest stars, from collapse so sudden, so violent, that it rips a hole in the rules of reality. They are not ancient, primordial beasts left over from the Big Bang, though some might be. Most are young, cosmically speaking, born just millions of years ago, in the hearts of galaxies, in the arms of star clusters, in the quiet between the stars, waiting, watching, pulling, and growing. You cannot see a black hole. Not really. Not the thing itself, because it gives off no light, no reflection, no color, no surface. But you can see what it does to everything around it. And that is how we map its anatomy. Like a shadow cast by an unseen object, we trace its outline by the glow of what surrounds it. So let's take it apart, piece by piece, layer by layer, starting from the outside and moving in. First, the accretion disk. This is the crown of fire that circles the black hole. It is not solid, not like a planet's ring. It is gas, mostly hydrogen, helium, traces of heavier elements ripped from a nearby star or pulled from interstellar clouds. This gas doesn't fall straight in, it spirals, like water circling a drain, but slower at first. As it moves inward, it speeds up. Friction between layers heats it. Not just warm, not just hot. We're talking millions of degrees. Hot enough to glow, not in visible light, but in X-rays. That's why we find black holes with X-ray telescopes. Chandra. New star. XMM Newton. They don't see the hole. They see the scream of the gas just before it vanishes. The accretion disk is also flat. Why? Because the material usually comes from one direction, like a star losing its outer layers. That gas carries angular momentum, meaning it spins. And as it falls, it flattens into a disk, just like pizza dough spun in the air, or Saturn's rings, or our own solar system. Spinning things flatten. That's physics. Above and below the disk, something even stranger happens. Jets. Twin beams of particles shooting out from the poles at nearly the speed of light, sometimes stretching for thousands, even millions of light years, brighter than entire galaxies. How? We think it's the black hole's spin and its magnetic field. The black hole drags space around, with it, like stirring honey with a spoon. That spinning space twists magnetic fields frozen into the accretion disk, and those fields act like catapults, launching charged particles up and down along the axis of rotation, where there's no gas, no resistance. So they fly unimpeded, carrying energy across the cosmos. These jets don't come from inside the black hole. Nothing comes from inside. They come from just outside, from the magnetic fury of the disk and the spin of the hole itself. Closer in, hugging the event horizon, is a region called the ergosphere. Only exists if the black hole is spinning, which most of them are, because stars spin, and when they collapse, they spin faster, like an ice skater pulling in their arms. So, a spinning black hole doesn't just warp space, it drags space around with it. The ergosphere is where that dragging becomes unavoidable. Even if you're trying to hover perfectly still, space itself moves beneath you. You are forced to rotate with the black hole. It's like standing on a merry-go-round that you can't step off. In this region, something wild is possible. You can steal energy from the black hole. Yes, seriously. It's called the Penrose process. Throw an object into the ergosphere. Let it break apart. One piece falls in, the other flies out with more energy than it came in with. Where did that energy come from? The black hole's spin. You slowed it down just a tiny bit and took the difference as fuel. This isn't science fiction, it's math, it's physics. And someday, far in the future, advanced civilizations might use it to power starships, to light cities, by mining the spin of black holes. Now, let's talk about what happens if you fall in. Not in a ship, not with shields, just you, floating toward the event horizon. From far away, you look normal. But as you get closer, something strange happens. Your feet feel heavier than your head, because gravity is stronger closer to the hole. So your feet are pulled harder, your head less, and your body begins to stretch, longer and thinner, like taffy, like spaghetti. That's spaghettification. Yes, that's the real scientific term, coined by Stephen Hawking himself. It's not gentle, it's violent. For stellar mass black holes, it happens long before you reach the event horizon. You'd be shredded atom from atom in seconds. But for supermassive black holes, like the one in our galaxy, the gravity changes more slowly. So you might cross the event horizon before you're torn apart. But don't celebrate, because once you're inside, there's no stopping, no turning, no calling for help. Space flows inward, faster than light, and you flow with it. And then there's time. Einstein told us gravity slows time. Near a black hole, that effect is extreme. If you hovered just above the event horizon for 1 hour, back on Earth, thousands of years might pass. You wouldn't feel it. Your watch would tick normally. But when you looked out, the universe would be racing, stars dying, galaxies colliding, civilizations rising and falling, all while you waited. This isn't theory. We've measured it. With satellites, with atomic clocks, gravity really does slow time. Near a black hole, it almost stops. So, to sum it up, a black hole is not just a dot of infinite density, it is a system, a machine, a cosmic engine, with parts an accretion disk glowing with stolen starlight, jets firing energy across the void, an ergosphere where space itself spins, an event horizon, the point of no return, and inside the singularity where our understanding ends. We cannot see it, we cannot touch it, but by watching what dances around it, we have learned to map its shape, to feel its pull, to hear its silence. Black holes are not all the same. They come in sizes, shapes of hunger, flavors of darkness. Some are born from single stars, others rule the hearts of galaxies, and a few might be older than stars themselves. Let's meet them, one by one. First, stellar mass black holes. These are the most common, the cosmic middle class, formed when giant stars die. Mass range 5 to maybe 100 times the mass of our Sun. Not huge in galactic terms, but dense, fierce, often found in binary systems, dancing with a living star, stealing its gas. That stolen gas glows in X-rays. That's how we find them, like Cygnus X1, the first black hole ever confirmed, discovered in 1971, or A0620W0, or V414 Cygni. We found dozens, maybe hundreds, in our galaxy alone. They don't wander looking for prey. They sit quietly until a star drifts too close. Then they feed, patient, efficient, deadly. Then there are the giants, the supermassive black holes, millions to billions of times the mass of the Sun, not born from one star, not even 10. We don't fully know how they got so big. Some think they started as seeds, heavy black holes formed in the early universe. Others think they grew by eating and merging over billions of years. Whatever the path, today they sit in the centers of almost every large galaxy, including ours, Sagittarius, a star, 4 million solar masses, tucked in the heart of the Milky Way, quiet now, but not always. Evidence shows it flared just a few centuries ago, bright enough to cast shadows on gas clouds hundreds of light years away. Other galaxies host monsters, like TON 618, a black hole 66 billion times the mass of the Sun, larger than our entire solar system, feeding on a swirling disk so bright it outshines its galaxy. That is a quasar, a supermassive black hole in its youth, gorging on gas and shining across the universe. But between these two lies a mystery, the missing link. Intermediate mass black holes, 100 to 100,000 solar masses, too big to come from a single star, too small to sit in a galactic core. Where are they, we think? Some might hide in globular clusters, dense balls of ancient stars like Omega Centauri, or in dwarf galaxies, like the one in NGC 1313 or ESO 243049. In 2020, LIGO detected a black hole merger producing a 142 solar mass black hole, the first solid evidence of this in-between class. Still rare, still elusive, but they exist, and they might be the stepping stones between star-sized and galaxy-sized monsters. Then there's the wild card, primordial black holes. Not born from stars, born from the Big Bang itself, in the first second of the universe, when density was extreme. tiny fluctuations might have collapsed directly into black holes. Some lighter than a mountain, others heavier than Jupiter. None have been confirmed. But if they exist, they could be part of dark matter, floating unseen through the galaxy, passing through Earth even now, harmlessly, too small to swallow us, too dark to see. But if we find one, it would rewrite the story of the early universe. So, to summarize, stellar mass, the survivors of dead stars; supermassive, the kings of galaxies; intermediate, the missing links we're just beginning to find; primordial, the ghosts from the dawn of time, each shaped by different rules, each leaving different footprints, each teaching us something new about gravity, time, and the fate of matter. Black holes are not passive. They are not silent tombstones floating in the dark. They are engines, violent, brilliant, transformative. They don't just destroy, they create, they shape, they rule. Let's begin with the brightest objects in the universe, quasars, short for quasi-stellar radio sources. But don't let the name fool you. They are not stars. They are supermassive black holes in their youth, feasting, gorging, devouring entire clouds of gas at a time. As matter spirals in, it heats up, not just warm, not just hot. We're talking trillions of degrees, glowing not in visible light, but across the spectrum: radio, infrared, ultraviolet, X-ray, gamma ray. The energy is staggering. A single quasar can outshine an entire galaxy of hundreds of billions of stars. And yet, the source is smaller than our solar system. That's the power of gravity. That's the fury of accretion. Some quasars shine from the early universe, over 13 billion years ago. We see them not because they're close, but because they're blindingly bright. They are cosmic lighthouses, telling us where the biggest black holes were growing when the universe was still a child. And then there are the jets. Not all black holes have them, but the ones that do. They paint across the sky. Take M87, a galaxy 50 million light years away. At its heart, a black hole 6.5 billion times the mass of the Sun. And shooting from its poles, a jet of pure energy stretching 5,000 light years. Visible in radio waves, in X-rays, even in optical light. What powers it? Spin, magnetic fields, and chaos. As the accretion disk twists and churns, magnetic field lines snap and reconnect, launching particles like slingshots along the axis of rotation, where there's no gas to slow them down, so they fly. At 99.9% the speed of light, carrying energy far beyond the black hole's grasp. These jets don't just glow, they sculpt, they heat, they push. They can shut down star formation in entire galaxies by blasting away the cool gas that stars are made from. No gas, no stars. So, black holes don't just eat. They regulate, they control, they decide how big a galaxy will grow. Now, let's talk about collisions. Black holes don't always sit still. Sometimes they orbit each other, especially after galaxies collide. Two galaxies merge. Their central black holes sink toward the center, and begin a slow gravitational dance, closer, faster, tighter, until they collide. Not with fire, not with light, but with ripples. In space-time itself, gravitational waves. Einstein predicted them in 1916, but no one heard them until 2015, when LIGO, the Laser Interferometer Gravitational Wave Observatory, detected a whisper. From 1.3 billion light-years away, two black holes spiraling, one 36 times the mass of the Sun, the other 29, merging into one, releasing more energy in that moment than all the stars in the observable universe combined. For a fraction of a second, the signal? A chirp, rising in pitch, in frequency, in intensity. Then silence. The first direct proof that black holes not only exist, but move, merge, and shake the fabric of reality. Since then, dozens more detections, some involving neutron stars, some involving mystery objects, each one a new piece of the puzzle. And that brings us back to kilonovae. Remember them from episode 4, when neutron stars collide? Well, sometimes one of them doesn't survive. It gets torn apart by its companion, which might be a black hole. That's what happened on August the 17th, 2017. GW17817. First, LIGO and Virgo heard the gravitational waves. A chirp from two neutron stars, spiraling. Then, 1.7 seconds later, Fermi and I Integral saw a gamma ray burst, short, sharp, powerful. Then telescopes around the world swiveled and saw the glow, the kilonovae, red, fading, rich in heavy elements, gold, platinum, uranium, the stuff in your jewelry, in your phone, in your bones, forged in the fire of a dying star's last moments. But this time, one of the partners might have been a low-mass black hole. We're still debating the details. But one thing is clear. Black holes don't just destroy matter. They help spread it. Across the galaxy, across time, across us. So, black holes in action. They are not quiet, not still, not lonely. They scream in X-rays. They blast in jets. They ring space-time like a bell. They forge the elements of life. They are chaos. They are order. They are death. They are creation. Black holes are not just strange. They are rebellious. They break rules, not because they want to, but because our rules were never built for places like this. At their edge and inside their core, our two greatest theories collide: Einstein's gravity and quantum mechanics. One rules the cosmos, the other rules the atom. But at the event horizon, they fight. And no one has won yet. Let's begin with the biggest mystery of all. The information paradox. It sounds abstract, but it cuts to the heart of reality. Here's the problem. In normal physics, information is never lost. Burn a book. The ashes, the smoke, the heat still contain all the information that was in the words. Scrambled? Yes. Hard to recover? Absolutely. But still there. Now, throw that book into a black hole. It crosses the event horizon, vanishes, and then the black hole slowly evaporates, thanks to Hawking, radiation, which we'll get to in a moment. But when the black hole is gone, where is the book? Where are the words? Did they disappear? If so, that breaks quantum mechanics. Because quantum mechanics says information must be preserved, always, forever. So, what's the answer? We don't know. Not yet. Some say the information is stored on the event horizon, like a hologram. Others say it leaks out slowly in the Hawking radiation. Others say it falls into a baby universe, or gets stuck in a firewall at the horizon. None of these are proven. All of them are being tested. This is the front line of theoretical physics. Now, let's talk about Hawking radiation. Yes, black holes glow. They are not perfectly black. Stephen Hawking figured this out in the 1970s. He combined quantum mechanics with gravity near the event horizon and found something astonishing. Empty space is not empty. It bubbles with virtual particles, pairs popping in and out of existence. Normally, they vanish instantly. But near the event horizon, one particle falls in, the other escapes. To the outside universe, that escaping particle looks like radiation, heat, light, energy coming from the black hole. So the black hole loses mass. Slowly, very, very, very slowly. A stellar mass black hole, it would take a Google years to evaporate. That's a 1 followed by 100 zeros. Far, far longer than the current age of the universe. But it happens, which means black holes are not eternal. They are born, they feed, they shine, and one day they vanish, leaving behind only questions. Then there's the firewall paradox, another headache from the clash of gravity and quantum theory. According to Einstein, crossing the event horizon should be uneventful, smooth, peaceful, no drama. But according to some quantum models, the horizon is a wall of fire, a searing sheet of energy that burns anything that touches it. Which one is right? We don't know, because no one has crossed and come back to tell us. This isn't just philosophy, it's a crisis. If Einstein is wrong at the horizon, then general relativity needs an upgrade. If quantum mechanics is wrong, then we're missing something fundamental. The truth, probably both theories are incomplete, and the real answer lies in something deeper. Something we haven't discovered yet. And then there's the singularity, the heart of the black hole, where density becomes infinite, where gravity becomes infinite, where time stops. Or does it? Infinities in physics are red flags. They mean our math has broken. Like dividing by zero. It doesn't mean reality is infinite. It means we're using the wrong equations. So what's really at the center? Some say a point. Others say a fuzzball, a tangled knot of strings from string theory. Others say a wormhole, a bridge to another place, another time, another universe. But none of this is proven. None of it is testable yet. The singularity remains hidden behind the horizon, behind the math, behind the mystery. And what about wormholes? You've seen them in movies, tunnels through space, shortcuts across the galaxy, or even time machines. Do they exist mathematically? Yes. Einstein's equations allow them, but physically, almost certainly, no. Because to hold a wormhole open, you need exotic matter, stuff with negative mass, which we've never seen, and probably doesn't exist. So, no. You cannot fly through a black hole and come out in another galaxy, or in the past, or meet your younger self. Black holes are not portals, they are prisons with no exits. So, where does that leave us? At the edge of understanding. Black holes are not just objects, they are challenges to our theories, to our tools, to our imagination. They force us to ask, what is space? What is time? What is information? What is real? And the answers? They won't come from telescopes alone, or equations alone. They'll come from both, from the marriage of observation and theory, from the courage to admit we don't know, and the curiosity to keep looking. You might be wondering, why should we care? Black holes are far away, silent, invisible. They don't pay taxes, they don't vote, they don't tweet. So why do they matter to us? The answer? They are not just cosmic oddities, they are teachers, architects, laboratories, and, surprisingly, protectors. First, they test Einstein every day, in ways no lab on Earth ever could. General Relativity was published in 1915. It predicted bent light, warped time, gravitational waves, black holes. All of it seemed too strange to be real. But black holes proved it. When we watched stars orbit Sagittarius, a star in the center of our galaxy, we saw their paths curve exactly as Einstein said they would. When we detected gravitational waves from colliding black holes, we heard space-time ringing like a bell in perfect harmony with his equations. When we saw the shadow of M87 star, its size, its shape matched the predictions down to the pixel. Black holes are not just objects, they are experiments running in the sky, testing the deepest laws of reality. And so far, Einstein is still winning. Then there's galaxy evolution. Black holes don't just sit in the center, they rule, they control, they decide how big a galaxy will grow. Here's how. When a black hole feeds, it doesn't just glow, it blasts. Jets and winds shoot out at nearly the speed of light. They slam into the surrounding gas, heating it, pushing it, blowing it far away. That gas, it's the raw material for stars. No gas, no new stars. So the black hole shuts down star formation. It puts a cap on the galaxy's growth. Too many stars, too much chaos. The black hole turns on and cools things down. This is called feedback, and it's why galaxies don't grow forever, why they have the shapes they do, why ours is calm and spiral, and not a bloated, messy blob of newborn stars. Without black holes, galaxies might be wild, unstable, short-lived. With them, they are balanced, structured, long-lasting. We owe our cosmic neighborhood to a quiet monster, sleeping in the dark. Now, let's talk safety. Because someone always asks, could a black hole swallow Earth? Short answer, no. Not even close. The nearest known black hole, Gaia BH1, about 1,500 light-years away. That's 90 quadrillion miles. You are more likely to be struck by lightning while winning the lottery, while being bitten by a shark in the middle of a desert. It's not happening. Even if, by some impossible magic, a black hole replaced our sun, Earth wouldn't get sucked in. Not right away, because gravity depends on mass, not on what kind of object it is. A black hole with the mass of the sun. It would pull exactly as hard as the sun does. Earth would keep orbiting, but it would be dark and cold and dead. So, the danger isn't the gravity, it's the absence of light and heat and life. But again, this is not a real threat. There are no black holes roaming toward us, none on a collision course, none hiding behind the moon. You are safe. Your children are safe. Your cat is safe. Black holes are not cosmic vacuum cleaners. They don't suck. They pull, like the sun, like Earth, like any mass. You have to get very close to fall in. And nothing nearby is that close. And then there's inspiration. Black holes remind us how much we don't know, and that's a good thing. They push our technology, our telescopes, our computers, our math. To see a black hole's shadow, we had to turn the entire planet into one giant telescope, the Event Horizon Telescope, linking dishes from Hawaii to Spain to Antarctica, processing data for years, solving problems no one had faced before. That kind of effort, it doesn't just give us pictures, it gives us new tools, new algorithms, new ways to see the invisible. Those tools, they'll be used in medicine, in AI, in climate science, in ways we can't predict yet. Black holes don't just teach us about space. They teach us how to solve impossible problems. And finally, perspective. When you see a black hole, when you understand its power, its silence, its mystery, you realize something. We are small, not just in size, but in time, in knowledge, in certainty. And that's beautiful. It means there is still wonder, still discovery, still awe. In a world that sometimes feels mapped and measured and monetized, black holes remind us the universe does not owe us answers. It offers questions, and the joy is in the chase. So yes, black holes matter. Not because they threaten us, but because they challenge us. Not because they are loud, but because in their silence we hear the echo of our own curiosity. We have seen the shadow. We have heard the chirp. We have mapped the glow. But we are not done, not even close. The next chapter in our understanding of black holes is just beginning, and it will be stranger, deeper, more beautiful than anything we've seen so far. First, sharper eyes. The Event Horizon Telescope gave us our first glimpse, but that was just the beginning. Now we're building the next generation. More telescopes, better resolution, higher sensitivity. Soon we won't just see a blurry ring, we'll see structure, swirls, knots, shadows moving across the disk. We might make movies of gas spiraling toward the horizon, of hotspots flaring as magnetic fields snap, of the black hole's shadow wobbling as it spins. This isn't science fiction. It's the plan. Within this decade, we could have the first real-time footage of matter vanishing into a black hole. Then there's LISA, the Laser Interferometer Space Antenna, not on Earth, but in space. 3 spacecraft flying in a triangle, millions of miles apart, linked by lasers, listening not for light, but for ripples, gravitational waves, but not from small black holes, not from stellar crashes. LISA will hear the giants, supermassive black holes merging in the hearts of colliding galaxies, events so powerful they shake the entire universe, and LISA will hear them years before they happen, because these black holes spiral for centuries, slowly, gracefully, sending out low-frequency waves like the deep hum of a cosmic cello. Ground-based detectors like LIGO can't hear that. They're tuned for high notes. LISA hears the bass, and when it launches in the mid-2030s, it will open a new window on the universe, one we've never looked through before. Then there's the James Webb Space Telescope, and ALMA, and Chandra, and the Vera Rubin Observatory. Each sees a different piece. Webb peers into the infrared, watching gas heat up as it falls. ALMA maps coal dust swirling in the outer disk. Chandra catches the X-ray scream of the inner edge. Vera Rubin will scan the entire southern sky every few nights, looking for sudden flares, tidal disruption events when a star wanders too close and gets shredded. We'll catch dozens, maybe hundreds per year, each one a new laboratory, a new chance to measure spin, mass, gravity in real time. But the biggest mystery still lies inside. The singularity, the place where Einstein meets quantum mechanics and both break down. To solve it, we need quantum gravity, a theory that unites the very large and the very small. String theory, loop quantum gravity, causal sets, holography, all are candidates. None are proven. But black holes are the testing ground, because inside and at the horizon, that's where the two theories must shake hands, or fight to the death. Hawking radiation might hold the key. If we can measure the tiniest fluctuations in that glow, we might see quantum gravity at work. But it's faint, too faint for today's tools, maybe not for tomorrow's. And what about visiting one? Not with humans, not in our lifetime, but with probes. Breakthrough Starshot showed us the idea. Tiny gram-scale spacecraft pushed by lasers to 20% the speed of light. Could we aim one at a black hole? Not Sagittarius A star, too far, but maybe a closer one, like Gaia, BH1, 1,500 light-years away. At 20% light speed, it would take 7,500 years to arrive, too long for us. But not for the species, not for the dream. We could send cameras, sensors, clocks, to test time dilation, to map the accretion flow, to listen for Hawking whispers. It would be a message in a bottle, thrown into the dark, with no hope of reply. But sometimes the act of sending is enough. Sometimes the question matters more than the answer. And then there's the data, the simulations, the AI. We now simulate black holes with such precision they look real. Fluid dynamics, magnetic fields, radiation pressure, general relativity, all woven into code, running on supercomputers. And now, machine learning helps us find patterns in the noise, in the glow, in the ripples. AI is teaching us to see what our eyes cannot, to hear what our ears miss, to find black holes hiding in plain sight. So the future, it is not about bigger telescopes or faster computers, or smarter equations. It is about better questions, deeper wonder, louder curiosity. Black holes will not give up their secrets easily. But we will not stop asking, not because we must, but because we can, because we are the universe becoming aware of itself, staring into the dark and whispering, "What are you?" We began with neutron stars, tiny, dense, spinning, a city made of atomic nuclei, so heavy that a teaspoon would crush a mountain. Then we stepped deeper to quark stars, hypothetical, strange, where neutrons dissolve into soup, a sea of free quarks, still not proven, but possible. A bridge between the known and the unknown. Then magnetars, neutron stars gone wild, with magnetic fields so strong they could erase your credit card from halfway across the moon. Fields that twist space-time, that crack the crust, that scream in gamma rays. They are cosmic lightning, violent, brief, beautiful. Then kilonovae, the collision of two dead stars, sending ripples through space-time and fire through the sky, forging gold, platinum, uranium, the stuff in your wedding ring, in your phone, in your bones, born in the final moments of dying stars, scattered by gravity's kiss. And now, black holes, the end of the line, where gravity wins, where light surrenders, where time bends and breaks. They are not the opposite of stars. They are their final form, the last whisper of a giant's death, the quiet after the supernova, the shadow behind the fire. Look back at the journey. From degenerate matter to quantum soup, from magnetic monsters to colliding corpses, from glowing disks to silent singularities. Each step stranger, each step deeper, each step teaching us something new about matter, about force, about time, about ourselves. Black holes are not the end of science. They are the beginning of the next chapter. They are not walls. They are doorways, not to other universes, but to new understanding. They force us to question, to calculate, to imagine, to build, to listen, to wait. And in their darkness, we find not fear, but wonder, not emptiness, but potential, not silence, but a different kind of song, the song of space-time ringing, of particles escaping, of galaxies growing and calming under their rule, of elements scattered by their violence, of questions too big for one lifetime, too beautiful to ignore. Einstein doubted they could exist. Hawking showed they could die. LIGO proved they dance. EHT showed us their face. And still, we do not know what lies inside. Still, we cannot say what the singularity truly is. Still, we cannot unite gravity and quantum mechanics. And that is perfect, because mystery is not failure. It is invitation. It is the universe whispering, "Come closer, look deeper, think harder. You are ready." So, as this journey ends, remember this. Black holes are not monsters. They are mirrors, reflecting our courage to explore, our patience to wait, our humility to admit we do not know, and our stubborn, beautiful human need to find out. You have traveled from the edge of collapsed stars to the center of galaxies, to the boundary of physics itself. You have seen the invisible, heard the silent, touched the untouchable with your mind, with your curiosity, with your wonder. That is the real power. Not gravity, not light, not time, but you. The one who looked up, who asked, who stayed until the end. This is not goodbye. It is see you later. Because the next discovery, it might come from a telescope you help fund, from a theory you help test, from a child who watches this and whispers, I want to know what's inside. The universe doesn't fear the dark, and now neither do you. If this journey moved you, if you stared at the screen and felt small and vast and curious and alive, then you are not alone. You are part of something older than civilization. The human need to understand the sky. You don't need a telescope or a PhD or a lab coat to explore black holes. You just need wonder and the will to follow it. Start here with what's free. NASA's Black Hole Encyclopedia, ESA's Cosmos Portal, the Event Horizon Telescope's public gallery, all online, all waiting. No paywalls, no passwords, just knowledge, open like the sky. Want to go deeper? Try citizen science. Projects like Gravity Spy, where you, yes you, help LIGO scientists classify gravitational wave signals by looking at patterns on your phone, on your laptop. You become part of the discovery. Not a spectator, a participant. Read, watch, listen. Books like Black Holes and Time Warps by Kip Thorne. Documentaries like Einstein's Quantum Riddle or The Farthest or Into the Universe with Stephen Hawking. Podcasts like The Supermassive Podcast or Daniel and Jorge Explain the Universe. All made to turn mystery into understanding. Without math, without jargon, just clear, beautiful storytelling. Talk about it at dinner, in the car, on a walk. Ask your friends, what do you think is inside a black hole? You'll be surprised by the answers and by the wonder in their eyes. Science grows when shared, not stored, not hoarded, but passed like a story around a fire. Subscribe, support, share. If this series sparked something in you, then someone else is waiting for that same spark. Share the episode, tag a friend, leave a comment, ask a question, debate the answer. That's how curiosity becomes culture. That's how wonder becomes movement. And if you can, support science. Donate to public observatories. Fund student internships. Advocate for space funding. Buy a kid a telescope or a book or a poster of the M87 star image. You never know whose life you might change, whose future you might launch. The next Einstein, the next Hawking, the next Katie Bowman, who helped build the algorithm that showed us the first black hole. She might be 8 years old, sitting in a classroom, staring out the window, wondering what's out there. Your support, your sharing, your curiosity, that's the fuel that lights her path. So, thank you for watching, for wondering, for staying until the final frame. You didn't have to, but you did. And that is everything. This series? It was never about black holes. Not really. It was about you. The one who looked up, who asked, "What is that?" Who refused to look away, who chose wonder over worry, curiosity over comfort. So keep looking up. Even when the sky is cloudy, even when the news is loud, even when life feels heavy, look up, because above you there is darkness, yes, but inside that darkness there is light, there is mystery, there is music, there is you, part of it, made from it. Searching within it, some mysteries are not meant to be solved. They are meant to be chased, to be carried, to be passed from one generation to the next. Black holes. They are one of those mysteries, and now they are yours.